Hi guys, this is Santan. Today I'm going to show a presentation on RTD, LDR and LM35 sensors. Coming to RTD sensors. A resistance thermometer or resistance temperature detector is a device which used to determine the temperature by measuring the resistance of pure electrical wire. This wire is referred to as a temperature sensor. If we want to measure temperature with high accuracy, RTD is the only one solution in industries. It has good linear characteristics over a wide range of temperature. The variation of resistance of the metal with the variation of the temperature is given as R of T is equal to R naught into 1 plus alpha of T minus T naught plus beta into T minus T naught and so on, where RT and R naught are the resistance values at T degree Celsius and T naught degree Celsius respectively. Alpha and beta are the constants which depend on the metals used. This expression is for huge range of temperature. Now for small range of temperature, the expression can be RT is equal to R naught into 1 plus alpha of T minus T naught, where alpha is temperature coefficient of resistance. RTD devices, copper, nickel and platinum are widely used metals. These three metals are having different resistance variations with respect to the temperature variations. That is called resistance temperature characteristics. Platinum has the temperature range of 650 degrees Celsius, and then the copper and nickel have 120 degrees Celsius and 300 degrees Celsius respectively. The figure shows the resistance temperature characteristics curve of the three different metals. For platinum, its resistance changes by approximately 0.4 ohms per degree Celsius of temperature. The purity of the platinum is checked by measuring R100 by R0, because whatever the materials actually we are using for making the RTD, that should be pure. If it will not be pure, it will deviate from the conventional resistance temperature graph. So alpha and beta values will change depending on the metals. Next, construction of resistance temperature detector or RTD. The construction is typically such that the wire is wound on a form or notched mica cross frame to achieve small size, improving the thermal conductivity to decrease the response time, and a high rate of heat transfer is obtained. In the industrial RTDs, the coil is protected by a stainless steel sheath or a protective tube, so that the physical strain is negligible as the wire expands and increases the length of wire with the temperature change. If the strain on the wire is increasing, then the tension increases. Due to that, the resistance of the wire will change, which is undesirable. So we don't want to change the resistance of wire by any other unwanted changes except the temperature changes. This is also useful to RTD maintenance while the plant is in operation. Mica is placed in between the steel sheath and resistance wire for better electrical insulation. Due to this less strain in resistance wire, it should be carefully wound over mica sheet. The figure shows the structural view of an industrial resistance temperature detector. Next, signal conditioning of RTD. We can get this RTD in market, but we must know the procedure how to use it and how to make the signal conditioning circuitry, so that the lead wire errors and other calibration errors can be minimized. In this RTD, the change in resistance value is very small with respect to the temperature. So the RTD value is measured by using a bridge circuit. By supplying the constant electric current to the bridge circuit and measuring the resulting voltage drop across the resistor, the RTD resistance can be calculated. Thereby, the temperature can also be determined. This temperature is determined by converting the RTD resistance value using a calibration expression. The different modules of RTD are shown in below figures. In two wires RTD bridge, the dummy wire is absent. The output taken from the remaining two ends as shown in the figure. But the extension wire resistance are very important to be considered, because the impedance of the extension wires may affect the temperature reading. This effect is minimizing in 3 wires RTD bridge circuit by connecting a dummy wire C. If wires A and B are matched properly in terms of length and cross section area, then their impedance effects will cancel, because each wire is in opposite position, so that the dummy wire C acts as a sense lead to measure the voltage drop across the RTD resistance, and it carries no current. In these circuits, the output voltage is directly proportional to the temperature, so we need one calibration equation to find the temperature. Expressions for a 3-wire RTD circuit. If we know the values of Vs and V0, we can find Rg and then we can find the temperature value using calibration equation. Now assuming R1 is equal to R2, we get the following equation. If R3 is equal to Rg, then V0 is equal to 0 and the bridge is balanced. This can be done manually, but if we don't want to do a manual calculation, we can just solve the equation 3 to get the expression for Rg as below. This expression assumes when the lead resistance RL is equal to 0. Suppose if RL is present in a situation, then the expression of Rg becomes as shown below. So if there is a error in the RTD resistance value because of the RL resistance, that is why we need to compensate the RL resistance as we discussed already by connecting one dummy line C as shown in figure. Next, limitations of RTD. In the RTD resistance, there will be an I square R power dissipation by the device itself that causes a slight heating effect. This is called as self-heating in RTD. This may also cause an erroneous reading. Thus, the electric current through the RTD resistance must be kept sufficiently low and constant to avoid self-heating. Now, coming to LDR sensor. A light dependent resistor is also called a photoresistor or a cadmium sulfide cell. It is also called a photoconductor. It is basically a photocell that works on the principle of photoconductivity. The passive component is basically a resistor whose resistance value decreases when the intensity of light decreases. This optoelectronic device is mostly used in light varying sensor circuit and light and dark activated switching circuits. Some of its applications include camera light meters, street lights, clock radios, light beam alarms, reflective smoke alarms, and outdoor clocks. Coming to the structure and working of LDR. The snake-like track shown below is the cadmium sulfide film which also passes through the sides. On the top and bottom are metal films which are connected to the terminal leads. It is designed in such a way as to provide maximum possible contact area with the two metal films. The structure is housed in a clear plastic or resin case to provide free access to external light. As explained above, the main component for the construction of LDR is cadmium sulfide, which is used as a photoconductor and contains no or very less electrons when not illuminated. In the absence of light, it is designed to have a high resistance in the range of megaohms. As soon as light falls on the resistor, the electrons are liberated and the conductivity of the material increases. When the light intensity exceeds a certain frequency, the photons absorbed by the semiconductor give band electrons the energy required to jump into the conduction band. This causes the free electrons or holes to conduct electricity and thus dropping the resistance dramatically. The equation to show the relation between resistance and illumination can be written as R is equal to A into e power A, where E is the illumination, R is the resistance, and A and small a are constants. The value of A depends on the CDS used and on the manufacturing process. Values usually range between 0.7 and 0.9. Variation in resistance with changing light intensity can be shown in a graph as below. Most common type of LDR has a resistance that falls with an increase in the light intensity falling upon the device. The resistance of an LDR may typically have the following resistances. You can therefore see that there is a large variation between these figures. If you plotted this variation on a graph, you would get something similar to that shown by the graph shown above. Coming to advantages, LDRs are cheap and are readily available in many sizes and shapes. Practical LDRs are available in a variety of sizes and package styles. The most popular size having a face diameter of roughly 10 mm. They need very small power and voltage for its operation. Coming to disadvantages, highly inaccurate with a response time of about 10 or hundreds of milliseconds. Next, applications of LDR. There are many applications for LDRs, which include lighting switch and camera shutter control. An example can be LDR control transistor circuit. This circuit shows a simple way of constructing a circuit that turns on when it goes dark. In this circuit, the LDR and the other resistance form a simple potential divider circuit. When the center point of the potential divider is fed to the base of the NPN transistor, When the light level decreases, the resistance of the LDR increases. As this resistance increases in the relation to the other resistance, which has a fixed resistance, it causes the voltage drop across the LDR to also increase. When this voltage is large enough, it will cause a transistor to turn on. The value of the fixed resistor will depend on the LDR used, the transistor used, and the supply voltage. Coming to the next sensor, LM35 sensor. It is an integrated analog temperature sensor whose electrical output is proportional to degrees centigrade. It does not require any external calibration or trimming to provide typical accuracies. Its low output impedance, linear output, and precise inherent calibration make interfacing to readout or control circuitry especially easy. It stands for linear monolithic. It is a type of commonly used temperature sensor that can be used to measure temperature with an electric output comparative to the temperature. It can measure temperature in a better way than thermistor. It is used in industries and other commercial buildings where high accuracy of temperature measuring is needed. 35 temperature sensor is available in many different packages like T046 metal transistor like package, T092 plastic transistor like package, 8 LED surface mount S08 small outline package. The 2D model of the component T092 can be seen as below. In description of LM35 is as shown below. It has 3 pinouts. One is for VCC, the other is for output, and third is for ground. The features of LM35 sensor can be pointed as below. Working of LM35 sensor. It is a precision integrated circuit temperature sensor whose output varies based on the temperature. It is very small and cheap IC. It can measure temperature between -55 degrees to 150 degrees. It can be easily interfaced with any microcontroller that has ADC function or any development platform like Arduino. Power the IC by applying a regulated voltage like +5 volt to the input pin and connect the ground pin to the ground of the circuit. Now you can measure the temperature in form of voltage as shown in the figure. If the temperature is 0 degrees, then the output is 0. There will be rise of 0.01 volt for every degree Celsius rise in temperature. The voltage can be converted into temperature using the below formula. LM35 interfacing circuit. As such, no extra components required to interface LM35 to ADC, as the input of LM35 is linear with 10 mV per degree scale. It can be directly interfaced to any 10 or 12 bit ADC. But if you are using an 8 bit ADC like ADC0808 or ADC0804, an amplifier section will be needed if you require to measure 1 degree Celsius change. LM35 can also be directly connected to Arduino. The output of RM35 temperature can also be given to comparator circuit and can be used for our temperature indication or by using a simple relay, and it can be used as a temperature controller as shown in the figure. Coming to advantages. The LM35 sensor operates within the widest temperature range and is more precise compared to its two competitors. Nevertheless, it is not the possible measurement error that is critical to most IoT solutions. It is the maximum amperage and the output voltage. As you can see, it can be powered by sources of between 4 volt and 30 volt. The TMP36 requires sources of between 2.7 and 5.5 volts, and the DHT11 requires sources of between 3 volt and 55 volt. Thus, the first sensor is not compatible with some photon chips as the acceptable voltage for them is 3.3 volts. So the TMP36 is perfect for integrating into solutions that require working with temperatures between 0 degrees Celsius, because you won't be able to connect the LM35 to analog contacts on Arduino chips. If you need maximum accuracy for Arduino based solution that will be used indoors, the LM35 is your best option. If you need the additional feature of determining humidity levels, the DHT11 represents the best price quality ratio. Coming to disadvantages, there is power supply needed, slower in operation, self-heating, limited configurations, and temperature up to 150 degrees Celsius only. Next, LM35 sensor applications. It can be used in measuring temperature of a particular environment. It provides thermal shutdown for a circuit of component, monitoring battery temperature of any mobile devices, measuring temperatures for HVAC applications. Thank you for seeing this video.